So this section is all about bugs. When we talk about bugs, and by bugs I mean things like insects or other arthropods like ticks, we can talk about them in a couple of different ways. We generally do call them parasites, and we have some parasites that we call endoparasites, meaning they're inside parasites. They're inside the body of another organism. That would be things like tapeworms, roundworms, things that you can find on the inside. The other type of parasite would, of course, be the opposite of an inside parasite. It'd be an outside parasite. We call those ectoparasites. Things like ticks, lice, fleas that would be found on the surface of an organism but don't generally get inside of the organism's body. We can also classify parasites as obligate or facultative. By obligate, that means they have to, at least for some part of their life cycle, live inside of a host. And that generally is going to be most of the protozoan parasites, things like tapeworms. But we also have some parasites that we call facultative, meaning they can live outside of the host, and sometimes they can live inside the host. Normally they can live outside, but occasionally these organisms can become parasites. So things like a fungal skin infection. A lot of the fungi that cause skin infections normally just live in the soil, and sometimes they get on us and then they cause an infection. So they would be facultative parasites. We also have permanent and temporary parasites. A permanent parasite is going to stay in the host until either the host dies or the host takes some sort of medical treatment to get rid of the parasite. They may shed larvae and things like that, but the original parasite will stay in the host. Temporary parasites, mostly we think of the insects and ticks, things that bite and then leave. They don't stay on forever, they're short term. We also have accidental parasites, and sometimes humans are the accidental host. If the parasite gets in us, sometimes we're not very good for the parasite to live in, and so the parasite doesn't do very well in us. And then we also have a situation of hyperparasitism, where we have a parasite living within a parasite. And so an example of this could be something like malaria. So malaria is a parasite that you can find in mosquitoes. Mosquitoes are a parasite that feeds on us. So you can have that kind of hyperparasitic relationship. We'll have one more slide of terminology, and then we'll talk about some of the bugs that can bite. So a vector, when we use the term vector in biology, we're talking about an organism that moves parasites from host to host. Generally, especially in this section of the class, we're talking about insects or ticks, other arthropods. And when we talk about them being like that, when we have, a mosquito or a fly or a tick, we can even further break them down. And so sometimes you have, for example, you have to be bitten by the mosquito in order to get the parasite. Because when the mosquito picks up the parasite from another organism, the parasite does part of the life cycle inside of the mosquito. So that means that the mosquito is a biological vector. The parasite does part of its life cycle inside of that vector. On the other hand, we have what are called mechanical vectors. And these are vectors that can transmit disease, but the disease-causing organism is generally not living inside of the vector. It's often transmitted on the vector itself, or if it does go inside the vector, it doesn't do part of its life cycle. Maybe it goes through the digestive tract or something. The really classic example of an insect that can serve as a mechanical vector is a fly, right? Like just a house fly. There are other kinds of flies that bite and transmit disease and blah, 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 blah. I'm talking about a house fly. or a cockroach. We don't typically think of these things as something that's going to bite you and give you an infection. But we think they're dirty and we think they're gross because things like flies and cockroaches, they live on decaying matter, they get on poop, and they can pick up parasites or other pathogens just because of how they live. And what we worry about is let's say you're outside having a barbecue and a bunch of flies are outside because, of course they are. And they land on your food and you're like, ugh, that's really gross. And it is, because if they were on feces or on some dead animal, they could bring those pathogens on their bodies, and then they're like walking on your food and drop off those, pathogenic organisms. So that's a mechanical vector. Now, really commonly when we talk about arthropods as vectors, so arthropods are a biological group of organisms. They are invertebrates. They don't have a backbone, but they are considered animals. And you might remember from a high school biology class, or those of you who have taken a college level biology class, there's a group of arachnids. Arachnids have 8 legs and 2 body parts, a head and a cephalothorax. So it's like their throat and abdomen kind of combined into one. So ticks, spiders, scorpions, things like that. We also have insects. Insects are very common biological vectors. In general, insects have 6 legs in their adult form of their life cycle. 6 legs. They have 3 body parts. They have a head, a thorax, and an abdomen. And they may have 0, 1, or 2 pairs of wings. So those are the general differences between an arachnid and an insect. But commonly we just call them all bugs. And this isn't an entomology class, so I'm not gonna be real picky with you, but there's even a group of insects that are technically called the bugs. Not all insects are bugs. It's weird. But also some crustaceans. Crustaceans are also considered part of the arthropods. They generally have 10 legs. Sometimes the front legs are modified into pinchers, if you've ever encountered a crab. And they can serve as aquatic arthropods to transmit disease. So first we'll start with some of the arachnid-transmitted infections. I always hesitate when I say this is my favorite, because it sounds really creepy when I'm like, oh, I love diseases, but I'm a microbiologist. I'm teaching a class called Revenge of the Killer Microbes. You probably already think I'm just a little bit creepy anyway, so there you go. But I did my PhD on this particular bacterium, Borrelia burgdorferi, which is the bacterium that causes a disease called Lyme disease. Lyme is named after a city in Connecticut, which is why it's spelled with a Y instead of an I, like the fruit. It is the most common arthropod-borne disease in the United States. Worldwide, definitely not. But in the US, it is our most common arthropod-borne disease, and it's transmitted specifically by ticks. And there are very special classification of ticks called hard ticks belonging to one particular genus. So there aren't a ton of ticks, considering all the ticks in the US. There's only a couple of different species that can transmit Lyme disease, but it's still very common. Generally, what we see when a patient develops Lyme disease is they will have this rash. They call it a bullseye rash because it looks a lot like a bullseye. And this right here represents the site of where the tick bit the patient. And as the tick bites, the bacteria move from the salivary glands of the tick into the host, in this case a person, and the bacteria will spread. And you'll see this tissue reaction as the bacteria spread. Eventually the rash goes away, and if left untreated, in the US, Lyme disease often causes symptoms of arthritis, and that's what they're trying to show you here in one of the large joints. So this is the joint of a knee. You can see how swollen it is. Rarely in the US, but in places like Europe, it's far more common that Lyme disease can also cause nervous system involvement and cardiac complications. It's not unheard of in the US, it's just not quite as common. Now, sometimes when you talk about Lyme disease, people do talk about what they call chronic Lyme disease. And there can be a controversy about whether Lyme disease is really a persistent infection. And so what I mean to say by there's a controversy is we don't doubt that people still experience symptoms years after the initial infection. That is not in doubt. If people have arthritis, people have arthritis. If people don't feel well, people don't feel well. I don't question that. The question in the scientific community is whether or not the bacteria are still there, or is it like almost an autoimmune type of complication where the bacteria have been cleared either through antibiotics or through the immune system, but now the body is overreacting to the fact that the bacteria used to be there and are causing the same symptoms. So that's more the debate. And it's relatively easy to treat with antibiotics. The bacteria grow pretty slowly, so you sometimes have to take antibiotics longer than you might think, like for a few months. But there's not a lot of antibiotic resistance, so it should be pretty easy to treat. But like you see here on the slide, about 25% of patients still complain of symptoms even when doctors can't find the bacteria anymore. So, are the bacteria still there and we just can't find them? Or is there something else going on that's causing these patients to still feel sick? Maybe some sort of autoimmune complication. Another infection that can be transmitted by ticks causes Rocky Mountain spotted fever. So this is a bacteria called rickettsia. These are what we call intracellular bacteria. They live inside the cell. So what we're trying to show you in this image here, this is a eukaryotic, a host cell. You can see the nucleus right here. And then all the little red dots inside are the rickettsia bacteria. One of the major symptoms of Rocky Mountain spotted fever, maybe you guessed from the name, you get spots and a fever. So you have a rash and a fever. So this person, you can see all of the red dots. That's the Rocky Mountain spotted fever. The bacteria live in the cells, and as they keep reproducing in the cells, those cells can die, and that can cause tissue damage. And unfortunately, even when you treat this infection, you can still sometimes see patients who die. About 3 to 5% of patients, even with treatment, might still die. The last tick-borne infection I want to talk about is called tularemia, or sometimes they call it rabbit fever. The bacteria that causes this disease is called Francisella tularensis, and it got its name. So the Francisella is the genus, tularensis is the species name. Francisella, like Francis was a person, Francisella, whatever, doesn't matter. But tularensis is named after the location where the disease was first discovered, Tulare County, which is down by Fresno. Symptoms of the infection really depend on where did the bacteria get into the body. So in this top image, you see a patient who has a lesion on the skin. So let's say maybe that's where the tick bit the patient. Depending on, again, how it got in, patients can experience lesions, fever, or sepsis. The bacteria can travel throughout the whole body. It can cause death through multiple organ failure, particularly if patients get what we call the pneumonic form. So pneumonic is generally going to be respiratory. We're talking about a respiratory form. And hopefully you're thinking, you just told us that this bacterium lives inside of ticks. How do you get it in your lungs? How do you get a tick in your lungs? You don't get a tick in your lungs. What can happen is, and part of the reason they call it rabbit fever is this is sometimes also an infection seen in rabbits. And in people who hunt or otherwise work with rabbits, if the rabbit is infected and the tissue has kind of dried out a little bit, the bacteria can get in the air. They can be aerosolized, and then they can be inhaled and cause that pneumonic form. And that form is very, very dangerous. The bacteria can live inside of macrophages. Those are cells of our immune system, so they can not only not be killed by our immune system, they can live inside of our immune system. But the fact that the bacteria can survive being dried out and can be aerosolized and cause serious disease makes this bacterium a potential bioweapon. So in the US, the Department of Defense sponsors research to develop vaccines and cures for this infection. In the US, we do not develop bioweapons, but we study all of these organisms that could be bioweapons so that we could potentially develop treatments.